Guys, this section is all about anti-differentiation. Now, anti-differentiation is exactly what it sounds like. It's the opposite of differentiation. You're going backwards. You're starting with something that's already been differentiated, and you're finding the functions that differentiate to that function. So first of all, let's do an example of the function y of x equals 3x squared plus 2x plus 4. Now I want to find what is called the antiderivative of y of x. In other words, I want to find all the functions that differentiate to give me y of x. So find all functions that differentiate with respect to x. Differentiate to y of x. Well, I can see one of them just from observation, kind of. So I know that if I take the function y of x, so this is big Y of x this time, so capital Y of x. If I take the function capital Y of x, now when I differentiate, I subtract 1 from the power and bring the old power down. So I'm going to go backwards. I'm going to actually bring that old power back up again. So the first term is going to be x cubed, because when I differentiate x cubed, I get 3x squared. Similarly, I'm going to bring the old power back up again, and so the next term is going to be x squared plus what differentiates to 4? Well, 4x differentiates to 4. So I know that if I have y of x equals x cubed plus x squared plus 4 of x, then I know that big Y prime of x is equal to 3x squared plus 2x plus 4. So that's little y of x. Okay, so I found one of the functions that differentiate to give me y of x. I found one of the functions. However, I want to find all of them. To find all of them, I'm going to actually suppose that there are two of them that differentiate to give me y of x. So let's suppose that I got two functions. We have y1 of x, so that's big Y1 of x, and we got big Y2 of x, such that big Y1 prime of x is equal to big Y2 prime of x equals little y of x. So these two functions both differentiate to give me the function little y of x. Well, if they both differentiate to the same thing, that means their derivatives are both equal. In other words, this tells us that big Y1 prime of x minus big Y2 prime of x is equal to 0. So big Y1 prime of x minus big Y2 prime of x equals 0. So if I let z of x equal y1 of x minus y2 of x, then that tells me that z prime of x, and since differentiation is linear, we can just differentiate each function separately, z prime of x, which is equal to y1 prime of x minus y2 prime of x, is equal to 0. So z prime of x is equal to 0. And that tells me that z of x must actually be equal to some constant c. Because if you differentiate a function and it's equal to 0, then that means that that function is not changing as x changes. So it's equal to a constant. Therefore, so since y1 of x minus y2 of x is equal to a constant, that tells me that y1 of x is equal to y2 of x plus some arbitrary constant c, So what we just worked out is that if two functions both differentiate to give the same thing, then they must differ by a constant. One of them has to be the other one plus some constant. That's what we just worked out here. So actually, all of the functions that differentiate to give me a little y of x all of the functions that differentiate to give me little y of x must be this function here, big Y of x, plus some constant. And that makes sense because constants disappear when you differentiate. And so what we say is that the antiderivative of little y of x dx is equal to big Y of x plus c, plus little c, where this constant is just some random number, because we want, what we've actually got here is the entire family of functions that differentiate to give little y of x. We want to include all of those functions, and actually to find all of those functions you just need to find any one of them that differentiates to give little y of x, and then add a constant to it, you'll get another one. So that must mean that big Y of x plus c is all of those functions. So another way to write this, do it on a separate board. Another way to write this is the integral of little y of x, which was 3x squared plus 2x plus 4 dx. Did I say integral? Well, you can say integral as well. You can say indefinite integral, but we're going to call it the antiderivative. So that's what I meant to say. The antiderivative of 3x squared plus 2x plus 4 dx is equal to big Y of x, which was x cubed plus x squared plus 4x plus c, some arbitrary constant c. Remember, we just need to find one function that when differentiated will give little y of x, and as soon as we've found one of them, all the other ones are going to be the same thing but with some constant added to it. So I could have also written this, by the way. I could have also written plus, I don't know, 10 plus c, because when I differentiate this thing here, when I differentiate x cubed plus x squared plus 4x plus 10, I still get 3x squared plus 2x plus 4. But it would be a little silly to write that, because actually this 10 is just some constant number. And if this is a random constant, then 10 plus c gives another random constant. So I may as well just include all the random constants together in one random constant. Okay, so that's it. Let's make a note of the theory. So I'll write this in general now. So given, okay, suppose big Y of x and little y of x are functions, and we have that big Y prime of x, so big Y differentiated with respect to x, is equal to little y of x. Then the antiderivative of little y of x dx means with respect to x, by the way. So the antiderivative of little y of x dx is equal to big Y of x plus c. Oops. Big Y of x plus c, where big Y of x is any function that differentiates to give little y of x. So this says the antiderivative of little y of x dx with respect to x is equal to big Y of x plus c, where c is an arbitrary constant and big Y of x is any function that differentiates to give little y of x. I just want to talk about this dx for a second. So suppose we've got the integral of little y of x dx equals big Y of x plus c. So this dx here, that means that we're integrating with respect to x. Now, does that make a difference? Well, actually, it sometimes can, yeah. Suppose that I have a function. Suppose that I have a function a times x, even. So it's my function is ax, and I want to integrate this thing. I want to find the antiderivative of this thing. So the antiderivative of ax, I can't actually answer that until I know which variable I'm integrating with respect to. So if I say the antiderivative of ax dx, then the answer is pretty easy. It's just ax squared divided by 2 plus some constant. Ax squared divided by 2 plus some constant, because when I differentiate this thing, I'm going to bring the 2 down, and then it will cancel with the 2 on the bottom, and I'll just be left with ax, and of course the constant will go away when I differentiate. So this is the family of functions that differentiates to give me ax when I differentiate with respect to x. Suppose instead I wrote the exact same thing. So suppose instead I wrote the antiderivative of ax dA. Well, then it's a completely different story altogether, because the antiderivative of ax dA, that means I'm integrating with respect to a this time. So the answer is actually going to be x times a squared divided by 2 plus c. So that's what that dx means. For now, it means we're going to integrate with respect to the variable x. Or if it says, say, dA, that means we're going to integrate with respect to the variable a. So that's a pretty important difference. Most of the time, though, I think it'll be pretty clear from the context which variable you're supposed to be integrating with respect to. Okay, that's it for this video. Thanks very much for watching. Don't forget to check out the notes on anti-differentiation and do the exercises at the back. See ya. Bye.